Hi, welcome to this lecture where we will work out the solutions of the problems given in assignment 1 for ordinary differential equations. So we were doing second order linear ordinary differential equations. And so we will work out the problems one by one and tell you how they're done. So the first problem that was given was to find the particular solution. So you have to find the particular solution for this given differential equation. Of course, this is with a sinusoidal input. Okay, and when we had worked out differential equations with sinusoidal inputs, and this was the general form that we had worked out in the lecture before while we were doing this. If this was a general second order linear differential equation with a sinusoidal input like this on the right hand side, we found out what the particular solution was going to be. It was a combination of all these constants and given in this particular form, and you can go back and check that. So this was really the formula that we had found out. Okay, and so the question is, can I change this into this form, and then I will have all the constants which I can put and I will get the particular solution. Okay, so what is this A sine, what is this right hand side? A sine small a t plus b. If I just break this up, if I expand this in terms of sine a plus b or sine theta plus gamma, whatever you call it, this is given by sine, you will get a cosine b from here and then a sine at. Okay, so this is the constant part. And you will get capital A, you will get a sine B and a cosine AT. You will get a sine B and a cosine AT. So this right hand side changes to this, where this, now if I compare this with this general form, you see the coefficient of sine AT, which is alpha here, this acts like alpha. This is constant, all constants. Capital A is a constant, small b is a constant. And the coefficient of cosine AT here is beta, so this is the beta. Okay, so that's all. So we have the alpha and beta in this formula. And so that's all we needed. Okay, so therefore, the particular solution for which is what we had to find for this differential equation would be, well, you can see the denominator is, so let me just be a little smart here. The denominator is common from both of them, so I can take that out and multiply it onto the left hand side. So what I can do is I have capital C minus a square whole square plus a square capital B square xpt. This would be equal to this thing, okay, where I will put, you have C minus a square. Now I know what is my alpha, it is this one. It is capital A cosine B, okay, plus small a capital B beta. What is beta? Well, beta is this. It's capital A sine B. Okay, this whole thing goes with sine AT. And this one with cosine AT, well, this has come to this side. I have put that across. So this is going to be C minus a square. Well, beta, what is beta? Beta is this, capital A sine B minus small a capital B. What is alpha? It is capital A cosine B, and this whole thing goes with cosine AT. Actually, capital A is common throughout. You can just take that out and divide by capital A on this side. Okay, don't want to keep extra factors here because anyway this thing is quite long. So can I group things here? You can see C minus a square is common. If I take C minus a square common, I have sine AT cosine B, and I have a cosine AT sine B, which really is sine AT plus B. Okay, so if I take C minus A square common from this one, cosine B sine AT, and C minus A square common from sine B cosine AT, I'm left with sine AT plus B. Because this will break up to give you sine AT cosine B and cosine AT sine B. Similarly, if I take small a capital B common from sine B sine AT and minus cosine B cosine AT, so if I take this common, that's the formula for cosine AT plus B. Okay. So I have this one. So therefore, it's quite easy. I just have to, so to find this small xpt, all I have to do is to divide, get this factor away, take the a to the numerator, bring this one down to the denominator. So I really have capital A by C minus A square. This C is a capital C, plus A square capital B square. Okay. And I have this whole thing on the right, which is C minus A square sine AT plus B plus small ab cosine AT plus B. That's your solution. Okay. Now there was another part to it where what would be the XP, what would be the general, what would be the particular solution if this is a case of no damping? Okay. In other words, capital B is 0. In the case of no damping, when capital B is 0, all I have to do is to put capital B equals 0 all throughout, wherever it is. And I'll get, so in the case that B is equal to 0, the case of no damping, XPT becomes what? Well, this is 0, so I have capital A over C minus A square whole square. And I have this one here, C minus A square sine AT plus B. And this capital B is 0, so this whole term is missing. So these two will cancel. So really what you have is capital A over C minus A square sine AT plus B. That was the first problem. Okay? All right. And this is the expression which you had to bring. It was said, show that the XPT, the particular solution would be this. Okay. All right. Let's go on to the next one. The next one was very much similar. So let me just write it down first. The next problem was to find, it was to take a cue from this problem. The hint was to really to apply this result. So the question was to find the general solution. So find now the general solution of, well, the capital B was minus 2. The capital C was just 1. And you really had, there was no small b, and there was only this, okay? So there was only a 2 and a t. In other words, what happened was capital A became 2, small a, the problem was small a plus small at plus b, so small a became 1, small b became 0, okay? Capital B turned into minus 2 and C turned into 1. That's it, okay? So I already have the formula for XPT in the general terms, okay? When there was A sine small at plus b, so all I have to do is to put these values in here and I'll have the solution. So let's just do that, okay? It's just that simple, okay? I'll just put the values in here. So, what are the values? Capital A is 2. This is 2. I'm trying to find a particular solution first, then we will go for the general solution, and combining the two, I will get the Then I'll find the complementary function. Combining the two, I'll get the general solution. So xpt first. Capital A is 2. Small a is 1 and capital C is 1. So this is really 0. Okay? 1 minus 1 square is 0. This is gone. And small a is 1. So I have 1. And b is minus 2. Minus 2 square is 4. So I just have a 4 over here. Okay, again I have a c minus a square. So c and a are the same, 1. So this is gone. This is 0. So this whole thing is gone. You're left with this part where a is small a is 1. Capital B is minus 2. So let me just write it here. Minus 2. And you have b is 0. A is 1. So you really have cosine t. And the 4 and the 4 will cancel. You're left with a negative sign, so minus cosine t. That's your solution for the particular, that's your answer for the particular solution. What's the complementary function? So to find that, we need the homogeneous solution, homogeneous form of this equation. The homogeneous form of this equation is x double prime minus 2x prime plus x is equal to 0. Just putting 0 on the right hand side. The auxiliary equation will be m square minus m 2m plus 1 is equal to 0, where m is an unknown constant which we have to find. This really gives you m minus 1 whole square equals 0. So the two roots m1 and m2 are the same. This really is the case of resonance. Okay, they're the same. So therefore, the complementary function, which I'll write h for the homogeneous, it's a solution of the homogeneous form, is just some constant c1 e to the power t and another constant c2 t e to the power t. Okay, so therefore x, the general solution is just this one. So let me just take e to the power t out. I have c1 plus tc2. This is the resonating factor, if you want to call it that. And then the particular solution was minus cosine t, and that's your general solution. All right, it's just an application of problem 1. Sorry, we were doing problem 2. This was problem 2. All right. What about problem 3? Problem 3 is just... Oh, okay. So problem 3 is one where we change the... So I'm going to rub all of this out. It's with a new kind of input. It's a product input where you have an exponential e to the power small at and some function v, which is a function of t. This is given. And you have to show that. So the problem tells you, the trial solution that the problem already suggests is that find the trial solution for the particular solution to be e to the power at some function u dot v. The problem is asking you to try this solution, and in the process you will know how to find u. Okay, so let's just do that. If I try the solution, I have to put x double prime, so I will have to differentiate this twice. If I differentiated once, so let's put that. So e to the power at u. I'm not writing ut because it's understood that u is a function of t. Double prime minus 2 e to the power at u 1 prime once plus e to the power at u. That's your x. Okay, and this should, if this is a trial solution, this should match up to e to the power at v on the right. Okay. So let's do the left-hand side. If you differentiate this once, I differentiate this one exponential first. So I get a down here, e to the power at u, and then I differentiate this one, so I get e to the power at u prime. This needs to be differentiated once more. Minus 2 times I have to differentiate this one, so which is really this. So I can write it down. A e to the power small at u plus e to the power at u prime. And then this one remains as it is, e to the power at u. Okay. This, again, as I said, should match up to e to the power at v. Okay. We need to differentiate this once more. What does it come to? If I differentiate this one again, I get I'm differentiating the exponential first. I'm getting an a square e to the power at u. Then I'm differentiating the u, so I'm getting a e to the power at u prime. Okay. Then I'm differentiating this one, the exponential first, so I get this one. So I can write 2 here. And I get a double differentiation on u, and this one remains the same, e to the power at u double prime, and the rest remains the same, e to the power at u plus e to the power at u prime plus e to the power at u. This gives me e to the power at v. Okay, right. I'll just group the terms. You can see that the exponential e to the power at is common throughout, even on the right hand side. So because the exponential is a non-zero factor, we can just get rid of it. Okay, there is no need for it. So let me just collect the terms. I'll collect the double prime terms first. There's only one, so u double prime is the only one. I'm not considering the exponential terms. If you want, I can rub them out for you. Okay. There you go. They're all gone. This one first. Then I want to group the u prime ones for the second. Okay. So u prime comes with this as a coefficient, 2a. And u prime comes with u prime, 2a, and u double prime is this one, 2a, u square is this, a square is, that's all right, that's with this. This one is from minus 2. Oops, I made a mistake. I don't think this was supposed to be minus 2. Was it supposed to be minus 2? I don't think I've changed the... Sorry, I was supposed to do the general form of this. So there was supposed to be B and C here. Right. So let's just change that. There was supposed to be a B here, and there was supposed to be a C here. Okay, so that's just what it is. Okay, there's a B and there's a C. This is a C, not an E. Okay, so this one, the minus 2 changes to a B, and this one changes to a C. Okay, all right, so now we have it. So this one is 2a, and from this one I get plus b, capital B, u prime, and then I group the non-differentiated terms, so I get an a square, I get this one, b, a small a and a capital B, and I get a C, this capital C. These are all with u, okay, and this gives me my v, and this is what it is. You had to show that you could find this u. So if you find the u from this differential equation, given whatever the input this v is, once you find u from here, you can put that back and this will be the particular solution. That's the essence of the problem, really. The reason this problem was given was not to check whether you can do the calculation. Of course, you can do the calculation, but the problem is actually telling you a method to find a particular solution for an input like this, where if you try a solution where you replace the given input by a general function, you see after trying this out, you will get an equation, you will get a second order linear differential equation in U with V as the input, and if once you solve this, you will get your U, and that if you put that back in, this will be the particular solution for this differential equation. And that's really implemented or asked to be implemented in the next problem. The next problem says, I'll just write it here, problem 4 says that you have to find this, you have to solve this differential equation. Or just find the particular solution. You have x double prime plus x prime plus x, okay, equals e to the power, so t squared e to the power t. So if you compare this with this, okay, really what you have is your b and c are both 1, your b is 1, your c is 1, and your small a is 1, your small a is 1, but your v, this function, which is a function of time, is t squared. All you have to do is to substitute this in this, and you will get your answer. So let's do that. So if I substitute, so this is your way to find your u. The way you find this u is these are the given values. So u double prime here remains what it is. So I have small a, which is 1, so I get a 2. I get capital B, which is 1, so I get a 3 u prime. And then I have 1 from here, because a is 1. I have 1 and a 1, which is 1 from here, and c is also 1, so I have a 3 u, which gives me t square on the right, because my v is t square. So I just have to solve this. How do I solve this? It's a polynomial on the right. So the trial solution for this equation, so the trial solution to solve this would be u would be a trial solution for the particular solution. I just need a particular solution, okay? It should be a function of t, because the input is in time. This is a second degree polynomial, so I'll put a very general second degree polynomial in here. And again, this was covered when we studied second order linear differential equations with polynomial inputs, okay? And this is what we have, this is a trial solution for this equation. Let's just try this. If you double differentiate u, you are just left with 2 alpha, okay, plus 3. If you differentiate u once, you are left with 2 alpha t plus beta. And if you don't differentiate u at all, you're left with what it is, plus beta t plus gamma equals, you better get t squared on the right, because this is a trial solution for this equation. Let's just group things. So I want to put the t squared term first, which gets 3 alpha as its coefficient. I want to do the t term second, which gets 6 alpha from here, and 3 beta from here. 3 beta from here. That's with t. What about the constant term? It gets a 2 alpha from here, a 3 beta from there, and just a 3 gamma from here. And this should give me my t square on the right. If you compare the coefficients, so this is really 0t plus 0. You should get, so I'll just do it here. So 3 alpha is 1. The coefficient of t squared is 1 on this side. So alpha must be 1/3. Okay. What about beta? This whole thing must be 0 if you're comparing the coefficients of t. So 6 alpha plus 3 beta must be 0. 6 alpha. We know alpha. So 6 alpha is 6 into 1/3, which is 2. Plus 3 beta must be 0. So that gives me beta to be minus 2/3. What about this? This must also be 0. 2 alpha is 2 by 3, 2 1/3, plus 3 beta is this. Okay, 3 and this 3 will cancel. You're left with a minus 2. And then you're left with a 3 gamma, which should be 0. Well, this works out to be 4 and a minus. That's minus 4 by 3. So gamma really becomes 4/9. Okay, so alpha, beta. So you have your alpha, beta, and gamma. Okay, so you have the particular solution for this differential equation. Okay, so really, can I just put what the particular solution is? Alpha turns out to be 1/3 of t square. Beta is minus 2/3 of t, and the last one is 4/9. That's your particular solution for this. And since this is the solution, we told you that you have to just substitute this u here, whatever you find, and that will be the solution for this equation. And since you're solving this equation, okay, you're solving this equation, your solution should be this with this u, okay, and your small a is 1, okay. So let's just write that down. Sorry, I rubbed that out. So your solution will be, your particular solution will be e to the power at. Well, in this case, I know a is 1, small a, and your u, which you find, which is 1/3 t square minus 2/3 t plus 4/9. I think that's it. Is this only about finding the particular solution? Yes, find the particular solution. Okay, one more final problem is problem 5. This was problem 4. Okay, let's just get rid of that. We've solved it. The final one is problem 5, which is to solve this. Again, you have to find the particular solution, x double prime plus bx prime plus cx, and on the right you have a polynomial input, at square plus b small bt plus small c. Remember, I'll write small c like this just so you don't confuse it with capital C. The question is, you have to show that this will be, and I'm calling this p, capital P. The right hand side is the polynomial. It's a polynomial of degree 2. It's a quadratic equation in T. So you have to show that this is the particular solution. Show that xp, the particular solution for this differential equation, is 1 over capital Cp minus b over capital C square dp dt plus capital B square minus capital C over C cube d2 capital P dt2. Okay, so we have to show that this is a solution, particular solution of this. In other words, if you put this in here, you should get this as the right hand side. That should be easy. I want to first find this one. So if I'm putting this here, so I'm double differentiating this, which gives me what? A double differentiation of, so these are all constants. So I get a double differentiation of P. Let me just write it like that. Minus capital B over C square. I get a triple differentiation of P because this has been differentiated once already. And B square minus capital C over C cube, I will get a 4-time differentiation of this. Okay. Now you know that this is the right hand side is a polynomial of degree 2. So triple differentiation and 4 times differentiations, they all produce 0. So this really is P double prime. And what is P double prime? this is capital C, mind you. I'll write C big here. P double prime is double differentiation, which is 2a. Okay, so there's just 2a on top. All right, what's your xp prime? That is differentiating this once. I get a 1cp prime minus b over capital C square. Now p double prime, because once it has already been differentiated, plus b square minus capital C over C cube, triple differentiation, because this has already been differentiated once or twice really. And this one produces 0 because there's a triple differentiation of a second degree polynomial. This one is 1 over C. What happens if you differentiate this once? You get a 2at plus small b. And what happens, minus capital B over C square. Double differentiation just gives me 2a. Okay, and this one produces 0. And xp is what it is. Okay, so if I just put all of them together, xp is xp. Okay, if I put all of them together, I'm adding this one, and this one. Really with a b here. So I just have to multiply the whole thing by a b. So I'm getting a capital B here and a b square. And I'm multiplying this one by c. So I'm getting a c here. I'm getting a c here. I'm getting a c here, which really gives me c square here. This one gives me a c here. And this one just makes it p. Okay, so if I add this one, and this one, okay, I should get this. In other words, p. So let's add them. You see, what is this really? This one is p minus capital B by C. This is the 2 small at plus b, because this is the one-time differentiation. And this one is capital B square minus C by C square, 2a, because this is a double differentiation. So if I add all of this, what remains is, you see, this one and this one will cancel. This one just cancels with this one. Okay. What else will cancel? This one, 2a over c, cancels with a minus 2a over c, because if you take the c, this gives me minus the c, and the c square will cancel once to give you a c on the bottom, in the bottom, and small 2a. So really, if I just write this out, so this is just going to be this with a 2a and a minus 2a over c. Sorry, there was a c square there. Yeah, so this will cancel with this, and this one will cancel with this. So really, you are just left with this p. Okay, so remember, I was adding this one, and c times this one, which is this. So you're left with p. So adding all three, I get p, which really is at square plus bt plus c, small c, and that's your right hand side. Okay, so this really is the particular solution for this differential equation. Now again, the purpose of the problem is not really to check whether you can solve this. It's very easy to do a bit of a differentiation and just needs a little bit of patience, that's all. But really, the thing here is that this turns out to be this is given in very general terms. Okay, this is given in very general terms, where any problem is just any second order problem, second order linear differential equation problem with a polynomial input like this, second degree polynomial input like this, will be just about giving you the specific a, b, and c's. And this really is giving you the formula. The formula was this. The formula was 1 over c. This was c square and this was c cube. Okay, this was what you had to show. You had to show that the xp was, the particular solution was this. if you get a problem with specific A, B, and C's, you, by just application of this formula, you will know what is the particular solution of this problem. Okay, so really this problem establishes a formula rather than to check whether you can do the calculations. It's pretty easy calculations. All right, I think this finishes the solutions of all the problems that were given in this assignment. I hope you did well in the assignment, and we'll see how that works out. Okay, all right, thank you.